Your 10-word AI prompt initiates a physical chain reaction that generates more heat than a jet engine, and we've built a liquid fortress to stop it from melting. We often think of artificial intelligence as something ethereal. We imagine it living in the cloud, a weightless digital entity that exists only in the form of code and logic. But the reality is far more grounded in the brutal laws of thermodynamics. Every time you ask an AI to generate an image, summarize a document, or write a line of code, you're triggering a massive thermal event. Beneath the sleek interfaces of our devices lies a sprawling infrastructure of silicon and copper that is currently engaged in a desperate war against heat. This is the story of the AI Leviathan and the extreme engineering required to keep the brain of the modern world from turning into a puddle of molten metal.
To understand the scale of the problem, we have to look at the heart of the machine. Today, the undisputed king of the AI era is the Nvidia H100 Tensor Core GPU. This piece of hardware is a masterpiece of human engineering, containing 80 billion transistors packed onto a single die. But these transistors come with a heavy price. As they flip on and off billions of times per second to process the complex mathematics of neural networks, they encounter electrical resistance. In physics, resistance equals heat. A single H100 chip can consume up to 700 watts of power. For context, that is more power than most household microwaves. And in a modern AI data center, we don't just use one of these chips, we use tens of thousands of them, stacked in racks, side by side. When you cluster thousands of 700-watt processors in a confined space, you aren't just building a computer, you are building a furnace. The thermal density of an AI server rack has reached levels that were unthinkable just 5 years ago. We have moved from racks that drew 10 kilowatts of power to monsters that demand 100 kilowatts or more. At this density, traditional methods of cooling are no longer just inefficient, they are physically impossible. The air simply cannot move fast enough to carry the heat away before the silicon reaches its thermal limit and shuts down. We have reached the end of the age of air. In the early days of computing, cooling was simple. You took a fan, blew it over a metal heatsink, and let the moving air carry the thermal energy away. This worked because air, while a poor conductor of heat, was abundant and free. But air has a very low heat capacity. To cool a modern Nvidia H100 cluster with air, you would need fans spinning so fast and moving so much volume that the noise would be deafening, and the energy required to move the air would rival the energy used by the chips themselves. This is the air wall. We have hit it, and we have hit it hard. Thermodynamics tells us that heat always moves from a hot object to a cooler one. The goal of any cooling system is to make that transfer as efficient as possible. Because air is so inefficient, engineers have turned to the most effective medium we have: liquid. Specifically, liquid cooling systems that use water or specialized dielectric fluids. Water has a heat-carrying capacity that is roughly 3,000 times greater than that of air. This means a small pipe of flowing liquid can remove the same amount of heat as a massive high-speed wind tunnel. There are two primary ways the industry is tackling this. The first is direct-to-chip cooling. In this setup, we replace the traditional air-cooled heatsink with a cold plate. This is a precision-machined copper block with tiny microchannels inside. Coolant is pumped directly through these channels, sitting just millimeters away from the GPU die. As the H100 works, the heat is immediately absorbed by the liquid and carried away to a heat exchanger outside the building. This method is highly efficient, but it requires a complex network of plumbing inside the server itself. Every connection is a potential point of failure. In the world of high-stakes computing, a single leak can be $1 million disaster. The second, and perhaps more radical approach, is immersion cooling. This is where we stop pretending that computers and liquids don't mix. In an immersion system, the entire server, motherboard, CPU, GPU, and all, is submerged in a tank of specialized non-conductive liquid. This liquid, often a synthetic oil or a fluorocarbon, looks like water but does not conduct electricity. Because the entire surface area of every component is in direct contact with the coolant, the thermal transfer is near perfect. There are no fans, no noise, and almost no wasted energy. It is the ultimate expression of thermal engineering, turning the data center into a silent, liquid-filled vault. But the cooling system is only one half of the equation. The other half is the power grid.
The AI Leviathan is hungry, and its appetite is growing exponentially. A single large-scale AI data center can now require upwards of 500 megawatts of power. To put that in perspective, that is enough to power a mid-sized city. We are seeing a shift in how data centers are built. They are no longer just buildings. They are heavy industrial complexes. In many parts of the world, the existing power grid simply cannot keep up. Data center operators are now being forced to build their own power substations, and in some cases, invest in dedicated small modular nuclear reactors just to keep the lights on and the chips cool. This leads us to a critical realization. The limit of AI is no longer just about who has the best algorithms or the most data. The limit of AI is now a physical one. It is a competition for electricity and thermal management. If you cannot cool the chips, you cannot run the models. If you cannot run the models, the intelligence age grinds to a halt. This is why Nvidia, Microsoft, and Google are now investing billions of dollars into thermal research. They aren't just software companies anymore. They are thermal and electrical engineering firms. Let's look closer at the physics of the H100 and its successors like the Blackwell B200. These chips are designed with thermal design power, or TDP, in mind. When a chip is under full load, it generates a specific amount of heat that the cooling system must be able to dissipate indefinitely. For the B200, that TDP has climbed to a staggering 1,000 watts. When you have a rack of 72 of these units, you are looking at 72,000 watts of heat in a space smaller than a refrigerator. If the cooling system fails for even a few seconds, the temperature inside the silicon will spike so fast that the internal circuits will physically expand and crack. This is the meltdown scenario that engineers stay awake at night worrying about.
To prevent this, modern AI data centers use sophisticated control loops. Thousands of sensors monitor the temperature at every point in the system. If a single GPU gets too hot, the system can throttle it, slowing down its clock speed to reduce heat output. But in the world of competitive AI training, throttling is the enemy. It increases the time it takes to train a model, which costs millions of dollars in lost productivity. The goal is to keep every chip running at its absolute thermal limit without ever crossing it. It is a high-wire act performed at the scale of atoms.
Then there is the question of where all that heat goes. Energy cannot be destroyed, it can only be moved. When we extract heat from a data center, we are essentially dumping it into the atmosphere. In many cities, this waste heat is becoming a valuable commodity. Engineers are now designing systems to capture the hot water coming off AI servers and pipe it into local district heating networks. This means the heat generated by your AI prompt could literally be used to heat a nearby apartment building or a public swimming pool. It is an elegant solution to a brutal problem, turning a byproduct into a resource.
However, the environmental impact remains a massive concern. The sheer amount of water used in evaporative cooling towers is staggering. A large data center can consume millions of gallons of water a day to keep its systems cool. In water-stressed regions, this creates a direct conflict between the needs of technology and the needs of the local population. This is driving the push toward closed-loop liquid cooling, where the same water is recycled indefinitely and heat is rejected into the air using massive radiators, much like the one in your car, but on a gargantuan scale. We must also consider the role of the power grid in this thermal dance. The grid was never designed for the concentrated, constant loads that AI demands. Traditional industrial loads like factories have cycles. AI data centers are always on. They represent a flat, massive line of demand that puts immense stress on transformers and transmission lines. We are seeing a transition towards grid-aware computing, where data centers can adjust their power consumption and cooling intensity based on the real-time health of the electrical grid. This requires another layer of AI just to manage the power and cooling for the primary AI. It is a recursive loop of machine-managed infrastructure. As we look toward the future, the challenges only grow. We are already talking about 1.5 kilowatt chips. We are talking about data centers that require a gigawatt of power. At this scale, the liquid cooling fortress will have to evolve. We may see chips with internal liquid cooling, where the coolant flows through microscopic channels etched directly into the silicon itself. We are moving toward a world where the distinction between a computer and a hydraulic system begins to blur. Why does all of this matter to you? Because the cost of intelligence is tied directly to the cost of cooling. The reason some AI services are expensive, or why there are limits on how many prompts you can send, is often not because of software limitations. It is because of the physical cost of the electricity and the cooling required to process your request. Every word the AI speaks has a thermal price tag. The AI Leviathan is a testament to human ambition. We have reached a point where our thirst for knowledge and automation has outpaced the natural limits of our hardware. We are no longer just writing code. We are bending the laws of thermodynamics to our will. We are building liquid-cooled cathedrals of silicon to house the most complex minds ever created. This isn't magic. It is the result of thousands of engineers solving the most difficult plumbing problem in history. It is the result of a global supply chain providing copper, synthetic fluids, and high-purity silicon. It is the result of a relentless pursuit of efficiency in the face of overwhelming heat. When you look at an AI-generated image or read a response from a chatbot, remember the liquid fortress. Remember the 700-watt chips and the massive heat exchangers humming in the desert. The intelligence age is not built on clouds. It is built on the brutal, hot reality of the physical world. And as long as we continue to push the boundaries of what machines can do, we will continue to find new ways to cool the fire of thought. The heat of intelligence is rising. The question is, can we build a fortress strong enough to contain it? As we move deeper into the 21st century, the success of our species might just depend on how well we can manage the thermal footprint of our own creations. The Leviathan is awake, it is hungry, and above all else, it is incredibly hot. Keeping it cool is the greatest engineering challenge of our time. We have explored the silicon, the liquid, and the grid. We have seen how a simple prompt becomes a thermal event. But this is only the beginning. As we push towards artificial general intelligence, the scale of this problem will increase by orders of magnitude. The fortress will need to grow, the plumbing will become more complex, and the relationship between humanity and its machines will be defined by the very energy that sustains them both. This is the reality of the AI Leviathan. It is a physical beast made of metal and fluid, breathing heat and exhaling intelligence. It is a marvel of the modern age, and its survival depends on our ability to master the heat. In the end, the most advanced intelligence on the planet is still subject to the same laws of physics as a boiling kettle. We have built a liquid fortress, and for now, it is holding the line. Thank you for joining us on this journey into the heart of the machine. The next time you send a prompt, take a second to think about the heat you're creating. And remember, it's not magic, it's engineering.